This is lesson 8, exercise 5G, solving simultaneous equations using matrices. And this will be the last lesson for the matrix component work. After this video, you will be doing the SAC, but because this has been pre-recorded prior to me even giving out the videos for this topic, I'm not too sure when this will be. You'll just have to keep tuned, or tune in. Keep tuned in. Yeah, we'll go with that. The learning goal for this one is to see how the inverse matrix can be used to solve 2 and 3 unknowns in simultaneous equations. And the success criteria is to know how to use your classified calculator to determine the unknowns of a context question through matrix inverse multiplication. So matrices at the start of the topic was considered one of the easiest things to do. It's this multitasking addition, subtraction, and scalar multiplication. And then you got introduced to matrix multiplication, and then that was a bit wacky, and you thought, no, okay, this is all right. A few extra steps, but then I can get used to that. Then you get introduced to inverse and identity matrices with determinants and different types of formulas that just kind of get pulled out of nowhere. All of those formulas do eventually come into play with this topic here. And we're now solving simultaneous equations, and this is what we did in chapter 3, I believe. And so we either used the substitution or elimination method when we did this, and that was, you guys remember that was quite a tedious task. With matrix inverse multiplication and using your classified calculator, it's a pretty simple thing to do. There is a bit of background knowledge that you need to know behind this, but there will be light at the end of the tunnel when we get through this. So before we learn to solve simultaneous equations, we need to understand how to transpose matrices. So let's pretend that A, B, and C represent a 2x2 matrix. If we get matrix A and we add matrix B, we get matrix C. That's pretty simple. We can just add the two matrices by getting each element and adding accordingly. But in this case, how do we find B? And this is going back to our algebraic manipulation days. If we want to get B by itself, we have to take away or eliminate anything that's around it. In this case, we have a plus A that's with it. So I'm going to minus A from it. And it decides to load. And it's probably just doesn't want to. Sorry, my stylus Photoshop just kind of had a bit of a mental breakdown, but I'm going to minus A from this side. Whenever I do to the left, I do to the right. Cancel, cancel. What I'm left with is just B by itself, plus B. And this is just equal to C minus the A tagging along. So we're just, in order to get B, we're going to find the difference between C and A in the form of a matrix. This can also work if we want to find A with this case. We have C minus A. So first I want to minus C, and whatever I do to the left, I do to the right. Cancel, cancel. I'm left with a minus A is equal to B minus C. If we just have this minus tagging along, pretty much I'm going to divide by -1. But all that happens is this A, everything on the other side becomes the opposite. So this is plus B becomes minus B, and this is a minus C, so it becomes plus C. And that's all there is to it when it comes to matrix adding and subtracting if we want to transpose it. But it doesn't necessarily work in the matrix world with multiplying, because multiplying has a different set of rules applied to it. So we can't do this. We can't do this, but we can use what's called the inverse of the matrix, which was in the previous topic, the previous video. So say for instance, A and B is equal to C, and we want to find B. I'm actually going to write this on the side here. So A times B is equal to C. Now in normal world, if this is just normal multiplication, if I want to get B by itself, I'll just divide by A, and B is equal to C divided by A, but we can't do this. So how do I get B by itself? Well, I want this to turn into a 1, 0, 0, 1. I want this to turn into the identity matrix. And how I do that is just by multiplying it by its inverse. So stick with me for now. I'm going to get A and B when it decides to rock up. There we go. Take your time. Not like we're in a rush or anything. Ah, the joys of remote teaching. Come on. Come on. I'm just going to pause again. As soon as I pause, it just decides to rock up. There we go. There's our AB. And what I'm going to do is I'm going to multiply that A out in the front by its inverse, A to the power of -1, because I know for a fact that A to the power of -1, there we go, I know for a fact that A to the power of -1 times A will give me the identity matrix 1, 0, 0, 1. And then when 1, 0, 0, 1 is multiplied with matrix B, we end up with just matrix B by itself. So what I've done is I've just forced this new matrix. And I have no idea what these matrices are. I'm not too sure. We'll eventually find out when we use real life context. But again, this rule applies. Whatever I do to the left, I also have to do to the right. So this C that's by itself, it's having an A inverse also being multiplied to it as well. Just like this. This in matrix world technically cancel out. So what I'll be left with is B is equal to the inverse of matrix A multiplied by C. In other words, if I wanted to get B by itself, just find the inverse of A and multiply it to what matrix C is. That is it. Now this kind of seems arbitrary if we're going to talk about in a matrix world, but this does tie in, where's the underline? I want to show you how delayed this is. Alright, I'm going to start beatboxing until it actually starts underlining. Now. Oh my goodness. Alright, I'm going to pause. Yay, a line. I didn't put just the one line. I wanted to show you what's going on. I've done so many weird random squiggles. There we go. Oh my goodness. Ah, freak. So annoying. Okay. So this is all we need to do. If I wanted again to do it to find A by itself, I'm just gonna get A, B is equal to C. I want to get rid of that B, so I'm just going to multiply it by its inverse, which is just B -1. And whatever I do to the left, I also do to the right. This in the matrix world cancels out. And what I will be left with is this A is equal to C times the inverse of B. Now, let's see how this actually is applied to simultaneous equations. So here, going back to the old chapter, solve to find x and y. We have 5x plus 2y is equal to 21 and 7x plus 3y is equal to 29. And remember, if you need a bit of a refresher, this is just saying, hey look, x and y at the end of the day are going to be these two numbers. When we plug these two numbers x and y in, when we multiply the x number by 5 and the y number by 2 and add them together, we should get 21 on the condition that that x and y value can also be substituted into the second equation, timesing it by 7 with the x and timesing it by y with the 3 and add it together, and I should get 29. The x and y only have one unique solution for each letter. There's no other letters that will work. What are those letters that we can substitute in? And then we go through the process of simultaneous equations with elimination, and it just gets tedious. We can just use this new process here. And let's see how this works. We're first going to rewrite the equation in matrix form. Now how we do that is I look at the numbers that are in front of the letters, and I'm going to put that, sorry, I just had another freeze again, in this matrix form by 2 by 2. So all we've done is just taken out these numbers. The second thing I'm going to do is I'm going to write a new matrix, which is just 2 rows, 1 column, and I'm going to put the letters that are being used associated with the numbers. In this case, it's just X and Y. Now right here, this is a multiplication. If I were to get the first row and multiply it with the first column, it will be 5 times X plus 2 times Y, which is actually what this sentence is saying here. And then again, I'll do it with 7 times X and 3 times Y, which is again what is here. Right here, this will be equal to 21 and 29. So I've just kind of manipulated this to mimic a matrix format of some sort, because it will suffice. It's the same thing. This is just saying this times this and plus this times this will equal to 21. Same thing with the 7 and 3. And the next thing we're going to do is we're going to name or label these matrices. Let's call this matrix here A, this matrix here X, and this matrix here C. So now that we've got this little indication on the side here is just saying, hey, how do we get X, matrix X by itself? Well, I want to get rid of this matrix A, so let's just multiply it with its inverse, A to the power negative 1, to turn it into an identity matrix. Because an identity matrix multiplied by any other matrix will result with that matrix in itself, regardless. But then whatever I do to the left, I also got to do to the right. So in other words, X will just be equal to A inverse multiplied by C. And how you write this out is just literally what it states. To get X, and remember X belongs to this matrix here, to get X, XY, I get matrix A's inverse, which is 5, 2, 7, 3, up by negative 1. And the calculator, we don't need to calculate this separately. We don't need to find this out separately. We can just put this straight in. This is just going to be multiplied with matrix C, which is 21, 29. 21, oh gosh, there we go, 21, 29. And then all we need to do is establish this in our class by calculator as matrix A, and this is matrix C. And then in the calculator, we're just going to type A to the power of negative 1 times C, making sure that we establish these two as matrices. So let's get our matrix out. Now, just add a protocol, default setting, always go edit and clear all variables. Clear all variables just make sure that anything that's established as an X or Y or whatever you've used has been cleared. And if you have a full screen, edit and clear all. Okay, let's put 5, 2, 7, 3 as a matrix. 5, 2, 7, 3. Put the matrix in, establish that, and we're going to put that as A. Execute that, and now the calculator knows that is A. We now want to establish the 21 and 29 as matrix C, so I've pressed this button here because it's just a column with two numbers, 21 and 29. Establish this as C. Execute that. So now that the calculator knows what A is and what C is, we want it to figure out what A to the power of negative 1, or the inverse of A, times C is. And I'll literally just write that out. So A to the power of negative 1, make sure you hit across, multiplied, my multiplication looks different, C, execute this, and it will say 5 and negative 2. Or in other words, 5 and negative 2. This is saying that the X and Y is equal to 5 and negative 2, or x is equal to 5 and y is equal to -2. So the process is really quick. Just establish this as your matrices, tell it what the inverse is, or get the inverse and multiply it by c, and you get a pair of solutions here. Alright, let's look at the practical applications of simultaneous equations. 2 more examples and then we're out of the woods with the lessons, or videos anyways. So, Mark buys 3 roses and 2 gardenias of $15.50, and then Peter buys 5 roses and 3 gardenias for $24.50. How much does each type of flower cost? So here are the steps. Identify the unknowns while choosing suitable pronumerals or letters. Write the equation and then follow the previous steps from before. Now I'm going to try to write this as small as I can because there's quite a bit of writing for this. So let's write this as the formula 3R, I'm going to use R for roses, plus 2G, G for gardenias, equals $15.50. There's equation 1. Now I don't need to label it. Before we just used to label it because that was the protocol. This time we don't need to. 5 roses and 3 gardenias is equal to $24.50. But now we want to write this in the format of a matrix. So let's get the pronumerals, the numbers in front of the pronumerals. So 3 and 2, 5 and 3. Next to this we'll have our column of letters that we're using, so R and G, roses and gardenias. And this is just equal to the column of what the numbers, or the total amount is, $15.50 and $24.50. And we'll just label this as matrix A, matrix X, and matrix C. To get matrix X, because that's the one we're looking for, it's just the inverse of A multiplied by C. Or in other words, RG is just going to equal whatever the inverse of 3253 is, multiplied by 15.5 or 50, same thing, 24.5, and then use our trusty calculator to work this out. So remember, edit, clear all, and edit, clear all variables, because we want to establish new x's and y's for this one. So let's put in math 2 matrix. We want to put 3253 for the first matrix. Establish that as A, execute that, and then matrix C, which is a column, that one there, that's 15.5 rather, not 15, down 5, 15.5 and 24.5. We want to establish that as matrix C. Execute that. And now let's just put in A to the power of -1, which is A's inverse, not -2, -1, multiplied by C. 2.5 or $2.50 and 4. So RG is equal to 2.5 and 4. So you would just state, therefore, roses cost $2.50 and the gardenias cost $4. Now if we were to substitute these values back into the question, or even into these two equations, we should get $15.50 and $24.50 respectively. But the process of doing that is really simple. It just took 3 lines, just putting some numbers into the matrix and just getting one of the inverses for them and multiplying it. That is it. And this also works. The reason why we look into this is because simultaneous equations has this really cool method, but of solving for 2 unknowns, but in this case here, we're going to solve something with 3 unknowns. And we don't venture into this for simultaneous equations because we don't have the required skills for this, but we can use matrix inverse multiplication. So, last example, a factory has 3 robots that assemble 3 different models of computers A, B, and C. Robot 1 assembles 3 models A, 2 models B, and 5 models C in 113 minutes. And there's Robot 2 and Robot 3 with the associated models and the associated minutes. And we want to know how long does it take a robot to assemble each of the 3 computer models. Now this question is a bit misleading, a little bit confusing. The question should really say, how long does it take for model A to be completed? How long does it take for model B to be completed? And how long does it take for model C to be completed? That's more of a appropriate question for this. Alright, so for now, let's put in what we do know. So 3 model A's, so 3A, 2 model B's, 2B, and 5 model C, 5C is equal to 113 minutes. And we have 3 unknowns now. 3 unknowns. And if we have 3 unknowns, by definition, we have to have 3 different equations. And we do, because there are 3 robots. 1 model of A, so that's just A, and 3 models of B. No C, so we just leave it as that, 56 minutes. And 2 models of B, and 1 model of C, so plus C, is equal to 40 minutes. So there are our equations, but now let's just write this in matrix format. This is going to be a bit bigger because it's a 3 by 3. We have a 3, we have a 2, we have a 5. 3, come on, don't take your time, just do it. So slow, 3, 2, 5, we have a 1, we have a 3. When there's nothing there for that pronumeral, you just put it as 0. And then again 0, 2, and 1. This multiplied by whatever pronumerals we're using. And this is equal to 113, 56, and 40. Matrix A, matrix X, and matrix C. If we want to find matrix X, we just find the inverse of A and multiply it by C. Or in other words, I have to write this a bit smaller now. Maybe C is going to equal 325, 130, and 021. The inverse of this multiplied by 1, 13, 56, and 40. This is all you'll need to write when it comes to the stack in regards to showing the working out. And then the class bit calculator will take over. And what you should get is A, B, C, and you should get a column of numbers. So edit, clear all variables. Let's put in the matrix. So it's a 3 by 3. 3, 2, 5, 1, 3, 0, 0, 2, 1. Establish that as capital A. I'm just going to write capital A on my keyboard. Boom. Column. And we'll just add one more. 113, 56, and 40. Establish that is matrix C. Boom. And find out what A to the power of -1, which is its inverse of that matrix, multiplied by C. We should get 11, 15, and 10. Or in other words, to create, for the robot to create model A, it takes 11 minutes. For model B, it will take 15 minutes. And for model C, it will take 10 minutes. And when you substitute these values into all 3 equations, you should get these answers respectively. I'm going to wrap it up, and that will be the end of this because I want to keep it under 25 minutes. Check your log sheet to see which questions you need to do. Remember, there is a worksheet that's also attached to this. And we'll have to tackle the SAC after this. I'm not too sure about the date, but you should be fine. Thank you for being patient with these stupid Photoshop. It can be a bit laggy sometimes, but it's the best of what I got. And until then, I will see you in the next video for the next topic. Telio.